All right, cool. Immunocto, Immunocto, the data set, is composed of about 8 million cells that you can use to train a cell typing model on H&E images. So really cool data set. It came out within the last year from researchers in the UK, and it essentially allows us to break the cell types down into 5 different cell types. Well, 4 different immune cell types plus kind of a throwaway category, because you need to be able to put all those cell types into categories. So the 5 classes that this data set allows us to identify or train with are CD4 positive T cells, CD8 positive T cells, macrophages, B cells, and then other, which is just any other type of cell. What was cool is that they were able to do this without the help of a pathologist by combining both an H&E image with a multispectral image, or an image that was produced by targeting multiple different types of proteins in the cells. And these proteins allowed the researchers to determine what the cell types were by what proteins they expressed. And then they were able to map those back onto the H&E image. And with all of that information combined, along with the nuclei masks that they obtained from Segment Anything, they were able to very accurately get these cell types together, apply them on the H&E images, and so researchers can directly, from the H&E images, deduce the cell types after training. I don't think that they actually released their trained models, but regardless, what we're going to do now is go through and train a model ourselves using this awesome data set. And if you don't have a lot of compute power, you can just take a subset of the data set, and that's totally fine. It'll work in the same way. But if you really want to hone in on making an awesome model, then of course using the entire data set would be preferable. Let's get into it. Okay, let's download the data. So navigate to the paper, we click on the PDF, we scroll down a little bit, and the link to the data set is on page 3 at Zenodo. And here we go. There it is. And it's all open source, very nice. Many downloads, as you can see. And each one of these lines is going to be a different patient. And then there's a CSV file that this is the CSV file. Down below we're going to have these tar.gz files, which we'll need to unzip, but that is fine. And there's a total of 40 patients in here. And then this is the CSV file that you can download from here, but we can preview that file up here and see that in that CSV file we have the patient listed, the class, so the cell type, the location of the X and Y coordinates of that cell, so the cell centroid, and this will be in terms of pixels. And then we have the name of the image and mask. So this provides both the H&E image as well as the nucleus mask of that particular cell, as segmented with Segment Anything. So we'll have 2 images that have this exact same name, but they'll be stored in 2 different folders. So we can go down here and you can go download all. I was not successful in that venture, so I had to go and download each of these individually. So you can just click download, create a new folder, Immunocto, and then we'll put it in there, and then we'll extract those later on using the command line. And then you just kind of go through and start doing that for all of these, unless you want to try your chances with this download all. Maybe it's good on other people's devices. And that is how you download the data for this. Okay, now we have the data downloaded. We have a folder for each patient. I've already gone and unzipped these, but I have a command in my notebook to assist with that, if you so choose. So we've got 40 patients here, down to CRC 40. We have our CSV file. Whoa, no, I do not want to open that. It's way too big. And we are ready to use our notebook. After I let you know, there's an H&E folder and a mask folder within each of these patient folders, as you can see here, and those are going to have the images in here. So H&E is going to be our H&E image, and then the mask corresponds to the nucleus. So the white is the nucleus, the black is the background, and you can kind of see here that these two match. So we have images. Here's the notebook. It's got fun links. It has the tar xvf function you can use to unzip stuff. And we're doing a data exploration here, just verifying that things are what we expect. We have the metadata folder here where each row is a cell, and we've got about 7 million rows in there. So that makes sense because there's about 7 million cells in this data set. We've printed the cell type classes here and the patients here, and kind of created some graphs so we can have a visual impression about some of this. Number of cells per cell class and the number of images per patient. Now we're going to define our PyTorch dataset class, and we are doing this in a slightly different way than we did before. We have our dataset code saved in a string variable. I've done that just so you can kind of see what's going on here. We're defining our dataset class as Immunocto dataset, and we are actually writing that to a file called dataset.py, and then we're pulling that in like we would a module. So from dataset, we don't even have to put dataset.py, import Immunocto dataset. So this will allow us to run it on a GPU. Now, example usage. Make sure with your transforms that you do the normalize consistent with the model that you selected. In our case, it's ResNet 50, so I looked on the PyTorch website to make sure that the mean and standard deviation values here were the same ones that were used to train the ResNet 50 pre-trained weights that we're going to be using. Then we load the data set in the data loader. We check these images to make sure that they are what we think they are. If we were pathologists, this would make more sense to us, but we can just hope for the best. Now, going down to splitting these up, because we gotta split them up so that we can validate and have a holdout data set, see how well it generalizes. We need to make sure that the patients are separated out from one another. Otherwise, it's kind of cheating because you're gonna have like, basically, if you have patient one in both your training set and your holdout set, then like the model's basically already seen that data. So you want to make sure you split the patients up between the splits. So if you have patients 1 through 4 in the training set, you don't want to have any patients 1 through 4 in your validation or your test set. Yeah, and then I also just downsampled the initial data set by a ton in order to account for the fact that I don't have a lot of compute at the moment. So in here, I only have 685 cells, and then I put it in the training loader and the validation loader, and see that I have 18 batches and 4 batches of 32 images each in there. I'm going to define our model right here, and the device, which is just conventional for PyTorch stuff. The device is either a CPU or CUDA GPU, and we're using the pre-trained weights. We have to adjust the input for the fact that we have a 64 by 64 pixel image instead of the default 224 by 224. So that's what we're doing in here. We're putting on a few other things to make sure that we could still use the pre-trained weights. And then finally, we're making sure that our output the number of output classes is consistent with what we want to be able to infer or predict. So we have 5 unique classes, so that is what we're going to want to funnel everything into, is an output of 5 numbers that represents the probability the model thinks that the image falls into. Like, what bin is, how confident is it, CD4, CD8, B cell, macrophage, or other cell? And so it's going to be spitting these 5 numbers out for every cell that it infers. And yeah, then we make sure that the model is on the device. We're defining the training loop. That's pretty much same deal, like all the time, every time. And then we're going to do a plot of the loss curve so we can kind of take a look at that as we go along. Maybe. Okay. Yeah. So now we can train the model. We're doing up to 100 epochs, but we can definitely stop it sooner. And when it does start training, it should show up in our output folder here as this loss plot. And it has not updated yet because I ran this before and it was February 19th apparently. But when it did that, you can see over these epochs that it trained pretty good. The training loss was going down over time, and the validation loss went down for a while, at least, so that was good, and I think it cut off at epoch 5. It would have trained better with more data, but that's fine. And we have stats in case we want to like make our own custom plot with R or some such thing. This is taking a while. I think I'm going to pause there and skip ahead so y'all don't have to wait for this. Okay, so the model is trained now, or at least somewhat trained. I stopped it after 5 epochs because I clearly don't have the patience for this. But we can see that the training loss and the validation loss both were decreasing over time over these epochs. So each pass resulted in a better and better model. Probably in all reality should have let it go, but here's the plot of this training. And yeah, it looks very steep. So if it were me on a normal day, I would just keep letting it go until it kind of, the slope evened out or even the validation came up a little bit and call it good. But here, good enough. So we are going to use this model. We're going to evaluate how well it was able to perform on the holdout data set, which we've defined by splitting up by patients. And so I don't recall precisely the number of patients in this data set, but that's what it's doing here. We're loading the Immunocto data set, Immunocto data set from the metadata file that's only a fraction of the original metadata file, and then just making sure that it only contains the patients that we want to have in here. And in this case, I don't know, we changed it to a batch size of 16. Didn't I have it 32 up there? I don't know. It doesn't really matter at this point because we're not training, so it's not a hyperparameter. It's only during training that the batch size can factor into things. And shuffling, we definitely don't need that here either, whereas shuffling is important to have during training. It is not, don't even bother with the evaluation. So, there we go. We're gonna load it up. We're gonna print the link, so there's only 2 batches in there, so up to 32 images, although the second batch could be less than that, I suppose. We're gonna go ahead and load our model, and we're using this syntax since it's a scripted model, so everything that we need is in this file, including the model architecture, but it doesn't allow us to necessarily pick up where we left off in case we wanted to use that and train the model more afterwards. I don't usually do that, so this works fine for me. If you want more details, go to the PyTorch website where they talk about saving and loading models. There's a lot more to it. And yeah, so let's load the model. We put it in eval mode so that it's not being inefficient with its compute. We're making lists of predicted and true labels, and we're going to make a data frame out of that so we can evaluate the accuracy percentage. And then we'll just take a look at what this evaluation data frame looks like. We've got a column for predicted label, a column for true label. And remember, these labels, these numeric labels, corresponded to the cell types. And 4 was other, 0 was CD4, etc., etc. So we see that there's a bit of mismatch here. So true, it got the first one right, predicted the first one right, and then it predicted the second one wrong, the third one wrong, and then the other 2 correctly. But yeah, this is just the first 5 rows. I guess we could take this off and just print the whole thing because it's not like it's very long. Yeah, so we have 25 total inferences. And we can make a confusion matrix out of that so that we can see if there are some sort of weird trends in what the model is predicting versus the true labels. And we can see here that, wow, okay, so the ideal situation would be for it to go all the way across here, light up blue, and then have 0 on everywhere else. But here, we've got a lot of problems. Mainly probably because there's just not a lot of data in this data set, and the evaluation data set is really small too. So it did do very well with predicting other on truly other cells. It had a lot more instances of that, so it makes sense. The other cells not so good, and the model accuracy is 69.2%, which, you know, when you think about it, sounds okay, you know, about 70% accurate. But then when you look at it, you're like, no, I wouldn't want to use this model. But, you know, that's fine. This is the training process. So you got to go through, you got to fix things, you got to shore things up, you got to change some hyperparameters. You want a lot more compute. But yeah, plenty of room for improvement for sure. But this data set is a great place to start if you want to try to infer immune cell types from H&E images. So I hope you have fun.